Hey everybody, time for some Chemistry 90 skills review. We're going to walk through some of the concepts from Units 1 and 2 just so we make sure we don't get rusty. We've got stoichiometry. We're going to go through significant figures, doing calculations, just basic one-step calculations with significant figures such as addition and subtraction, multiplication and division, and we're going to wrap things up with going through conversions. Now let's start out with stoichiometry. Stoichiometry is all about prediction. We're going to be predicting the amount of material that we're starting with, or the amount of material that we're going to be producing. And we're going to move on to this concept of ratios in stoichiometry, where we say, okay, is it a 1-to-1 ratio? Am I producing the same amount that I'm starting with? Or do I have a 1-to-2 ratio perhaps? Am I producing double of what I'm starting with in terms of moles? Now, to do stoichiometry, we're going to need two things. We're going to need a balanced reaction, so we need to hone those balancing skills for the various types of reactions that we covered, combination, combustion, and so on. And we're also going to need values in moles, not grams. So let's go over a few practice problems. To start out, we've got a basic stoichiometry problem. You'll note that it starts in moles, and we're given a reaction of 2 moles of magnesium plus 1 mole of oxygen gas goes to 2 moles of magnesium oxide. Now, this is already balanced for us. In a typical problem, if the reaction isn't balanced, you would be told beforehand. But since it's balanced, we can go ahead and jump in. Now, the question asks us, how much oxygen in moles is needed to fully react with 2.8 moles of magnesium metal? Now, to start this off, let's begin with the value we're given, 2.8 moles of magnesium. And we're going to look to the balanced reaction for a conversion factor. In this case, we have the coefficients of 1 mole of oxygen gas for every 2 moles of magnesium that we react. We're going to put magnesium on the bottom so that moles of magnesium cancel, leaving us with moles of oxygen gas, as shown here. So our answer would be 2.8 divided by 2, yielding 1.4 moles of oxygen gas. Now, moving up to intermediate stoichiometry, if we stick with the same reaction of magnesium reacting with oxygen gas, we could ask how much magnesium metal in moles is needed to fully react with 96 grams of oxygen gas. Now, in this case, it changes it up, and it gives us grams to begin with. Now, we said to do stoichiometry, we need two things. We need moles, and we need a balanced reaction. We have a balanced reaction, but we're starting in grams. We need to take this 96 grams of oxygen gas and convert to moles to begin with. To convert grams to moles, we use the molar mass of oxygen gas, which, taking 16 grams per oxygen, and it's O2, so we have 2 oxygens, we've got 32 grams of O2 for every 1 mole of oxygen gas. Dividing 96 by 32, our grams of O2 cancel. We end up with 3 moles of oxygen gas. So now we have moles, and we also have a balanced reaction, so we can jump straight into the stoichiometry. 3 moles of oxygen gas that we begin with. We look to the ratios that we get from the coefficients in the balanced reaction of 1 mole of O2 for every 2 moles of magnesium, and we set it up such that moles of oxygen gas cancel, leaving us with moles of magnesium for our final answer. 3 times 2 yields 6 moles of magnesium, which is the amount of magnesium metal required in moles to fully react with that 96 grams of oxygen gas that we started out with. Now, to take this a step further, we can move into limiting reactants. Limiting reactants are the varsity type problem, the hardest type problem that we're going to go into in Chem 90 for stoichiometry. It's based on this idea of running out of a particular material. Now, when you run out of one of your reactants, it's going to limit how much product you can make. We call this the limiting reactant, or the one that runs out first. Now, what we have extra of, we're going to refer to as the excess reactant. We have more of it than we need. So to pick out this type of problem, you're going to be given 2 or more start values, where in a typical easier stoichiometry problem, you would only be given 1 value to start with. So let's try one out. We're given the same reaction, relating the reaction of magnesium with oxygen gas, and it's asking how much magnesium oxide is produced from the reaction of 9.6 moles of magnesium with 9.6 moles of oxygen gas, and which reactant is limiting. Now, to find which reactant is limiting, we're going to need to find which is produced to begin with. So we have moles, and we have the balanced reaction that we're given, so we can jump straight into the ratios of the stoichiometry part of the calculation. We're going to have to predict how much MgO, or magnesium oxide, is produced based off of the magnesium and based off of the oxygen gas. So let's start with the magnesium and then we'll work our way to oxygen gas. We have 9.6 moles of magnesium. If you go to the ratio, it's a 2 mole of magnesium for every 2 mole of magnesium oxide ratio. 9.6 moles of magnesium, your moles of magnesium cancel. Multiply it by 2 and divide it by 2, we get back what we started, 9.6 moles of magnesium oxide, based off of magnesium. Now we need to repeat that calculation, predicting the amount of product made based off of oxygen gas. We look to the balanced coefficients for our ratios, and we see that for every 1 mole of O2, we're going to yield 2 moles of magnesium oxide. Our moles of oxygen gas cancel. When we multiply 9.6 times 2, we end up with 19.2 moles of magnesium oxide. So let's think about this for a moment. One predicts that we make 9.6 moles, one predicts that we make 19.2 moles. When doing a limiting reactant problem and faced with this kind of predicament, you're going to pick the smaller of the two amounts as the amount that's actually produced. So we're actually producing 9.6 moles of magnesium oxide because the amount of magnesium is limiting how much of our magnesium oxide we can make. You would say that magnesium is our limiting reactant because we run out of it first. Our excess reactant would be oxygen gas in this case.